Okay, so maybe we should move on to the next group on our list. And these are the UN, SUN groups. Okay. The SUN groups will be a subgroup of UN, so I'm considering them together. Okay, so let's consider, say, n by n matrices U such that they satisfy U dagger U is 1. Okay, so that means that U dagger is equal to U inverse. Okay, so these are, these matrices make the UN group. Okay, and it's easy to show that this condition, cuts down the number of independent parameters to half. So because UN matrices are complex valued, right? Because otherwise taking the Hermitian conjugate is not anything meaningful. UN matrices are, complex valued. So the number of parameter goes from 2n squared real parameters. This condition cuts it down to n squared. Okay, so the dimension of the dimension of the UN group is n squared. Now, if I look at the subgroup of, and it is a subgroup of UN that consists of all the unitary matrices. By the way, this is called, these matrices, this is called unitarity. So U stands for unitary. So the subgroup of UN that consists of all the determinant of U equals to +1, they form a group. They form a group and known as SUN, okay? S stands for special, which is this condition. Now, what are the generators like? So we are interested in the generators of SUN groups. And these are actually quite amazing, useful groups in quantum physics. Both in quantum physics, SU2 is the one that is very useful in quantum mechanics. SU2 is useful in quantum mechanics, but both SU2, SU3, and we actually consider U1 to be part of this series, are useful in particle physics. Okay. In fact, the standard model of particle physics has something called a gauge symmetry, and the symmetry of the theory is SU3 cross SU2 cross U1. Okay, so these two are the symmetries of the weak interaction and electromagnetism, and this is the symmetry of strong interaction, strong nuclear physics. Okay, let's look at the generators of SUN. So, so if you write an element of SUN as some exponential times I, where zeta is a set of real parameters, then U dagger is going to be E minus I zeta A T A dagger, right? Because this is just as if you do the series expansion of this thing, every term, I will flip its sign and T will become conjugated, Hermitian conjugated. On the other hand, U inverse is E minus I zeta A T A, right? So that if I multiply this guy and this guy, we get 1. So according to the unitarity condition, these two things are equal. And therefore, we see that TA, the generators, must be Hermitian. Okay? So this is one of the important properties of the SU and matrices. And this also is a clue as to why they are so useful in quantum mechanics, because in quantum mechanics, we know that all the observables are Hermitian operators, or they're Hermitian matrices, if you think in terms of Heisenberg's matrix mechanics. And therefore, you know, when you have an observable, exponentiating them gives you unitary transformations. So symmetries of quantum mechanics are actually generated by observers. So if, for example, a quantity is conserved in quantum mechanics, then you can show that there is a unitary transformation associated with that quantity, which is a symmetry of that quantum mechanical system. So for example, suppose that the momentum operator P, so that's a Hermitian operator in quantum mechanics, and suppose you have a system where momentum is conserved. So what does that mean? That means that under time evolution, momentum doesn't change. So this is 0. This implies if your Hamiltonian is a time-independent Hamiltonian, this implies that H commutes, H is the Hamiltonian, commutes with P. Okay, so, and you can show that this means that H is invariant under translation in space. That if you take a system and translate it in space, then that is a symmetry of your system. And if that is the case, then the momentum is conserved.
This is the Nurtura's theorem, right?
This is an example of Nurtura's theorem. Yeah. And this is actually something you should understand even classically. This is actually, Nurtura's theorem was actually a classical theorem originally. And the idea is, you know, if you have, even in say classical physics, say Newtonian physics, suppose you have a system which doesn't have any friction. But it has some potential like this, right? And the particle starts here, the system starts here, so this is the potential V of x, right? So of course, because you see, because of the potential, your system is not invariant under translation in space because there's a potential term. And therefore, you know that your kinetic energy or your momentum is not going to be conserved because there's going to be force on the system because the potential is changing with space, because what we call force is nothing but the gradient minus of the gradient of the potential, right? Okay. So let's go back to a discussion about the generators. So we have established for SUN and actually for UN as well, the generators are Hermitian, right? For SUN, we have an extra condition, which is the determinant of U must be 1. And we know from our formula relating the determinant of a matrix and the trace of its generator that this implies that the trace of the generator must be 0. Okay, so we see that SUN generators have, well, this is, the first one is true also for UN. They are Hermitian. So, for UN. And number 2, that they are traceless. Okay. So we can see that UN is going to be the bigger thing. So SUN will be some subgroup of UN, right? So there should be a relationship between UN and SUN. Okay, so this is our next topic, is the relationship between UN and SUN.
So I have a question. So applying the determinant condition, does it affect the dimensions?
Yes, it does, because it's
For example, I worked with like ON and SON. In that case, the dimensions didn't change.
Right. So UN is actually yeah. So the passage from UN to SUN, UN doesn't have those kind of discrete transformations in them.
Oh, that is because of the discrete transformation with the determinant doesn't reduce the.
Yeah, here UN itself doesn't have any discrete transformations. Okay, so for example, if you take U2, U2 will have say -1, right? And this is actually, this is a completely this is not a discrete transformation. On C2, right? This guy acts on C2, right? The 2x2 matrices act on C2. Like the vector space that UN acts on, it acts on some Cn, right? I mean, we'll talk more about what things act on when we talk about representation theory in the near future. Okay, let's figure out the relationship between UN and SUN. So the theorem is this. It's actually a very easy application of the first isomorphism theorem, is that if you take the direct product of SUN and U1, okay, then, and if you divide it by Z of n, that is isomorphic to UN. Okay, so this is the relationship. And the proof is very easy.
So it's a special case of the exam problem, I guess. Or the general case.
The general case of the exam problem, yeah. So the proof is very easy. So, let's construct an isomorphism, a homomorphism from SUN cross U1 to UN. So how do we do that? We take an element of SUN, let's call it U, an element of U1. Well, an element of U1, we can write it e to the power phi, right? So we can take this to UN, and the element is going to be e to the power I phi of U, right? Because if I consider this guy, if you look at it, if you take its, if U is, let's call this, say V. So, if I take V dagger is e to the power minus I phi, U dagger, right? So we see that V dagger, V is U dagger e to the power minus I phi. V is EI phi of U. Because U is unitary and these are just phases, we have 1. So
Sir,
yes.
I think there is an issue with this map, is that you won't actually get elements of UN by using this map, because I worked out the characteristics of elements of UN, and it says that like diagonally related elements must have a certain sort of phase difference, but if you write just U, the phase differences can be arbitrary, so that won't really give elements in UN. So that was a problem I also faced in the exam.
Okay, so I'm not exactly sure what you're talking about, but let me just continue, and you can point out what I'm doing wrong here, okay? So what I'm saying is that, I have verified that this is an element of UN. And if I take the determinant of V, I have essentially the determinant of EI phi and the determinant of U. Now this has the determinant +1, and this has determinant if it's in the e to the power I phi n, right? So, if I go back to my, matrix U dagger U, just one second, okay? Let me just pause. Okay, let me finish this now here, and then we can discuss more in detail what you're talking about, okay? So if I look at the U dagger U equals to 1 condition and take its determinant, then I have U dagger determinant U equals to 1, right? So the thing is that whatever its determinant, let's call it small u, this will be U star, right? And therefore this is 1. So we see that the determinant of U is a phase. And that's what we get here, right? The determinant of, say, UN is a phase. Okay, so now let's look at the kernel of this map. So let's look at the kernel of this map. And for that, what we say is that, all those elements that map from here to the identity here. So which means that e to the power I phi times U must be the identity. Now, if I take the determinant of this equation, what we find is the determinant of U is determinant of e to the power minus I phi. But the determinant of U is 1, and the determinant of e to the power I phi is e to the power minus I phi n. And therefore, we see that e to the power minus I phi has to be of the form e to the power 2 pi I over n. You can put a minus sign if you like. And therefore, this is an element of Zn. So we see that the kernel of that map is Zn. And therefore, SUN cross U1 over Zn is equal to UN.